Great. Well, my name is Galen McKinley. I'm the Deputy Director of the LEAP STC. We are really excited to have Libby Barnes from Colorado State University as our speaker today. Libby got her PhD at University of Washington in 2012, and then was a postdoc here at Lamont in Columbia, supported by the NOAA Climate and Global Change Postdoctoral Fellowship. And then since 2013, she's been at CSU as a professor of atmospheric sciences. Libby is a leading expert on climate variability and change. She's a pioneer in using data science tools to address climate dynamics, predictability, and to, in the context also of Earth system modeling. And her leadership and scientific pioneer has been recognized with many awards, including in 2014, the Holden Award from the AGU's Atmospheric Sciences Division, the 2018 NSF Career, 2020 Messenger AMS Award, and in 2021, the AGU's McIlwain Medal. So you're definitely in for a treat with this presentation today from Libby. And thank you everyone for being here. Thank you to Jihei for making it all happen, and to the other LEAP staff for making all this work. So
thank you. Thank you, Galen. Can you guys hear me? I think green means on, I think. Okay, I will warn who's ever in charge of the volume, it might be me, that as I continue, I get more excited and then I get louder. So you do have to let me know if I have to turn the mic down. All right, I can already tell. Who's in charge of the mic volume? Is that me? Can I turn it down? You don't know how.
It's okay.
Oh,
You're great. You're great. You're great.
You say that now. We'll see. Okay. So thank you for the invitation. I'm really excited. I think this is my first in-person seminar in a long time. So this is great. I get feedback and hopefully some excited faces at some point. So I'll tell you some, let's see, we have to get rid of that. But so today I want to talk to you about some of the work we've been doing on explainable AI. I realize that I've been told, the sleep audience is so diverse in their expertise. So some of this material will be boring for some of you and vice versa, not others. My hope is though, by the end, I inspire you to keep doing what you're doing. All right, so I'm a trained climate scientist. So I really think of doing climate sciences as we have this toolbox of lots of tools. And I really see personally machine learning as one of the many tools that we already use to do what we do. It's not going to be the one thing, it's not like we throw out the screwdriver once we get the hammer. They're all still important. But one of the fun things about being a part of this age right now in climate science is how do we use this hammer? How do we use it intelligently and correctly to get at questions we couldn't before? And so we're really the idea is to take in data from the Earth system, process it, and then hopefully do interesting things at the other side, right? And that's what so many of you are already thinking about now. I'm not going to go through sort of a review of what a neural network is, but just as a general reminder that we use a lot of neural networks in our work, and data goes in and a prediction typically comes out. And now all these connections that make it look so complicated are really just these linear plus a little bit of nonlinearity pieces that together make such a complex system. And the whole complexity and nonlinearity, at least the way I think about it, allows the network to learn many different pathways of predictable behavior. And I say it that way because in climate science, we think a lot about pathways of information flow. And once trained, the idea is we can go off and use this new tool to make predictions on unseen data. As a reminder, machine learning is not new for climate science. There's actually a paper from 1964. And if you look at the bottom right, that looks a lot like the picture I just showed you. All right. And in this paper, they're applying it directly to meteorology predictions, so forecasts. All right. So this goes way back. And then it's not like it was done in the 60s and forgotten about. Machine learning has played a role in climate and weather science decade upon decade. Just right now, I would say it's exploding. Not that it's new. There are lots of examples of machine learning for climate science, many of them done by people in this room. So I updated my slide if you've seen me give this spiel before. Laura's like, I've seen this 9 times. Okay, but this is a focus actually on climate predictability and prediction rather than just for climate science in general, because I think it's actually pretty interesting all the ways, even for this very narrow topic, climate prediction that machine learning may or can or is being used. For example, just pure downscaling for regional impacts of climate. For example, under climate change is important. Predicting errors of forecast systems. I think there's a ton of work to be done in this area, both for weather forecasting, but all the way to climate timescales. Post-processing of model output. In this case, I mean like climate models, trying to understand how to put their predictions together to make the best prediction for the real world. Model parameterization, I don't have to say anything about that to people in this room. And then general statistical model predictions, which is what most of my talk is going to be about, because that's what my group does. But also, I want to point out climate change communication, I think, is going to be an area we're going to see a lot of machine learning applied to. That is, once we get our really cool science results, how do we communicate it to people who are non-scientists? And AI, I think, is going to have a role to play, especially because our brains are so, we really like pictures. And so this idea of saying your house might flood is very different than showing somebody a picture of their house flooding. And that's where things like machine learning might be able to help us make those images. All right, I just want to point out before I keep going that I have a group doing a lot of this work, and I just want to point out many of these graduate students, postdocs, and research scientists are doing a lot of the heavy lifting. It's not like I'm up here writing all the code. Although if you know me, I do love code. So I do write some code all the time. So why might we use AI for science? Maybe I don't have to say this for this audience, but I do think it's good to have sort of this list in your back pocket. And someone's like, why are you using these tools for this particular question? I put it into 3 categories. One is to do something better. So again, convective parameterizations, we're still working on them. Maybe AI can help us make them more accurate. But there are other reasons. And I think a lot of people sometimes get stuck on that one. Another is maybe we already know how to do this thing, but we just want to do it faster or we want to do it cheaper. This is another example where AI, I think, is going to have big implications, especially for example, forecasting. And then finally, the nerd in me, the scientist really wants to learn new things, right? Even if it's not better, and even if it's slower, and even if, well, if it's more expensive, I'm probably out. But learning something new is what I'm in this job for. And I think AI has the ability to help us start to poke at it once we've gotten it working and figure out what it has learned so we can learn it too. All right, so I'm going to go through some examples. This one is the oldest. So again, I really do apologize to those of you who've seen me talk before. They didn't get to see it again. But it does lead into really framing how we're thinking about using AI for our climate work today. So the first is on finding 4 signals in the presence of climate noise, which is always with us and honestly is what keeps me confident I will have a job. All right, so climate change. We're aware that the climate change and anthropogenic CO2 is causing temperature to increase. And if you look at that increase, so this is a change in temperature from the end of the 21st century and 1850, 1900, and everything's red. Climate is warming. A few things of interest: the Arctic is warming faster than the rest of the globe, and the land is warming faster than the oceans. This seems pretty straightforward. But this is, for example, what those temperature sort of perturbations look like in 2021. That's a very different picture. What makes this so different? The other was an average over many, many climate models. And so it killed all that noise and gave us that big one signal, right? Climate warming. We don't get to do that with the Earth. We only get one of them. So because of that, even though the Earth is absolutely warming, it also has noise on top of it. So when we look at this, we have to ask the question, well, which of these blobs is that signal we just saw and which is the noise? And you don't get just to look at the red bits and say that's the signal, because they could also be a little bit warmer or colder on top of this trend because of internal climate variability. So the community has been attacking this problem for decades. This is not a new question by any means, but we're using machine learning to try to get at this a slightly different way. So I will point out the types of questions we're going to ask is, what are the patterns of change that we see? What geophysical variables are you interested in? What's the timing of these patterns emerging from that background noise? Do we see them already? Do we need to wait another 10 years before we're sure that that's that climate change signal? And then from a climate model evaluation perspective, which of these climate models are, quote, doing it correctly? That's an incredibly hard problem, but again, how can we start to attack or continue to attack that? So this is recent work actually by my PhD student, Jamin Rader, who is leveraging some other work that we did in the past, which is training a neural network to take in maps from climate models. So in this case, these are seasonal average surface temperature and precipitation maps. So think of the year you were born. There are 4 maps from a single climate model of the precipitation, 1 for each season and 4 for temperature. Then think of another year, there's another set of 8 for each. Does that make sense? We're putting that into the network. And what do we want it to predict? We want it to predict what year is it, which seems pretty weird. All right, so can it tell us what year those maps came from? Okay, so how is it going to do this? Well, if you think about it, we're doing this over many climate models that all have different climate noise at different times. So the only way it can reliably predict the year is to find signals or indicators that are consistent from across climate models for every year. That is, maybe it learns, for example, it doesn't actually learn this, I've checked, but it learns that Mount Pinatubo went off in 1991, and it learns, when I see Mount Pinatubo, like eruption, that must be 1991. Okay, that's the type of thing it has to learn here. That is, it has to learn the force change due to climate change in the presence of internal climate variability. So this is an example of what a result looks like. So we train the network, it appears to do okay, do all of our things, and the true year of every set of maps is on the x-axis, the predicted year is on the y, and you can see that after about 1970, 1980 or so, it really lines up along that one-to-one line, suggesting the network has started to learn patterns that indicate what year it is. All right, do you see how it's sort of blobby before that? So when I first started working on this with a computer scientist, he thought this was our activation function somehow being embedded in our results. So for the he's like, oh, it's ReLU. And actually, it has nothing to do with that. From a climate science perspective, what this is saying is, in the 1930s, the force response was so weak that the network had absolutely no idea what year it was, and every year looked like every other year. It wasn't until about 1970, 1980 or so that it finally goes, I can tell what year it is, and from then on, does a great job. All right. And then finally, you see the white dots there. This part was fun and actually terrifying. So I was so excited. This was my first machine learning project. This works Jamin's, but the first time we ever did this setup. My first one, and someone said, well, you should push the obs through. Because this learned on climate model output. Every year in the real world, we have a map. Put it through and see how it does. And you're like, oh, great, it's going to fail miserably, right? And maybe for temperature, this isn't surprising, but it did a great job. What that means, that's pretty powerful. What that means is this neural network from learning from climate models alone has learned indicators of a changing climate amidst climate noise. It gets 1 year at a time, right? Every year it's completely on its own. No time series information. And it's still then able to get the correct year in observation. And one of the reasons I really love this problem is no one can argue with me that there's uncertainty in the observations of the year. Okay, they can argue with the maps themselves, but we know what year it is every year. All right, so we've also done this for precipitation as well. And one of Jamin's results was maybe not surprisingly, he put in maps of precipitation and temperature together, and the network does a better job and detects force change earlier than if it was only given each variable on its own. So really finding signals that go together. And it's not that it's all from temperature. It's that precip also included some information that was new. All right, so who's here thinking this? Why would we predict the year? So I've just done a nice job. It looks pretty good after about 1970. Who's going to ever pay me money or give me, a grant to predict what year it is? We know this already. Shouldn't we be predicting something we don't know? And I'll say maybe, but this to me is the fun part of being a scientist, is I get to be weird and try and be creative. And at the end of the day, I don't really care what the year is, but what I care is how did the network know what the year was? That's the interesting part of this entire setup, not the prediction. So how could we learn what regions are most relevant? And that's where this opening the black box comes in, or leveraging explainable AI. So looking and trying to investigate how the network came to its conclusion. So this concept is not new either. There have been quite a few papers, even in climate and geoscience, that have come out in the past few years on this topic, specific for our field. Computer science has been working on this for longer than that. And the whole idea is how do we go in and find explainability methods that tell us the network's decision-making process. So there's a lot of different kinds of explainable AI techniques, and I'm happy to talk about them during questions. One particular technique I want to talk about now is the attribution method. And the way these methods work is after you've trained your network and you make a prediction, in this case, take a picture of a cat, and the network has to predict the probability of there being a cat in the image, and the network says it's 0.8. You say, good. How did you come to that decision? Global attribution methods take that 0.8 and propagate it back to the network and ultimately produce a heat map to show you the regions of the input that were most important or relevant for that output. Now, in this case, the results are very boring. So the network looked where there's a cat to determine there's a cat. Surprising no one, right? Okay. So for those of you who haven't seen this before, hopefully at least one of you, this is one of my favorite set of slides ever. Okay. So again, we want to use, let's use this to figure out the strategies of the network. Okay, so network was trained to predict if there are horses in these images. And there are horses, at least they're sort of blurry, but I think they're there. Okay, and the network also said there were horses in these images. How did it come to its conclusion? We can use these methods and make a heat map of where it looked. All right, and the colors are horrible, but just look at the red, yellow bits. And you can sort of squint and convince yourself that the heat maps may line up with the horses. So the network's sort of looking where there's a horse to predict that there are horses in the images. I can already see some people like, I don't think so. All right, well, just wait. Okay, sort of horse-ish regions. Let's do another set of three more horses. The network also correctly predicted all three of these had horses. So how did it come to its conclusion? And in this case, we see something different. The brightest spots have nothing to do with the horses. What do they have to do with? Somebody. Yeah, the bottom left-hand image is actually the website where these horse images were scraped. So it turns out that most of the horse images in this data set came from one German website that always put their copyright symbol in the bottom left. So the network is really good at horses. Now, you might say this is a really effective strategy. It's getting the right answer. But again, as scientists, we're like, we feel very uncomfortable about this because if I put a picture of my horse, my horse in the network, it's going to probably get it wrong. Okay, and this is what many of us are terrified about when we start thinking about machine learning for scientific applications. So in this case, XAI is really helpful for identifying problematic strategies. And really, I think it's critical as scientists to start to feel like it's getting those right answers for the right reasons. So to put that down in words, I have people at multiple times at talks where I show this say, I really am not a scientist. I don't care how it comes to its conclusion. Just give me a good prediction. I once had someone in charge of a lot of water in the West on the phone tell me, I don't care if you use a magic 8-ball. Just give me a forecast. I don't care where it came from. Okay, I need it to be good though. And so I'd like to stress that even if you think you don't care how it did it, you don't still care how it did it. Okay, and the reason is, if you don't care, sooner or later you could get burned, right? And get terrible answers because the thing is garbage. All right, so why might we need explainable AI? One is to gauge trust, right? Get a feeling for, hey, again, as scientists, is it getting the answers the way we think they should? Now, could that bias us certain ways? Absolutely. Certainly something for discussion. Okay, but I think this is one piece. Another is to fine-tune and optimize the network. We don't always know exactly the right way to set our networks up from the first place. So we're trying to find like, how is it coming to its decisions? And if it's using that information, maybe I should set it up a slightly different way. And we actually use this a lot in just designing the whole approach. And then finally, learning new science, like I just showed, the idea that maybe we don't care about the prediction itself, but we want to know how that it got there to learn something new. And so returning to this problem that Jamin set up, we want to ask the question, which regions are relevant for correctly predicting the year? So we can use these attribution methods to propagate the prediction back to the network and create a map that looks something like this, telling us the regions of the globe that were most helpful for predicting the year. In this case, the June, July, August temperature map. Okay, so you can come up with indicator patterns like this. They can vary in time, but they can also, for example, make the same one for precipitation. What's cool about this one is, to me, I'm like, it's just using temperature. It's the most obvious variable, but it's not. It's actually leveraging precip too. I showed that earlier. So I want to know which regions is precipitation providing information that temperature didn't. Something's happening there. And this is that map showing you those regions of the globe where precipitation has unique information from that of temperature. And I will point out the signal to noise map, which is the more standard way that we would think about this problem. It's certainly similar. Places with big signals and small noise should certainly be used and leveraged by the neural network. Don't get me wrong. But there are other regions of the globe that also pop up as important regions and indicators. Okay, so we've done a lot of work using XAI to leverage, I am getting louder, sorry, leverage imperfect climate models and constrain future projections. But I'd also like to go to slightly shorter timescales and think a bit more about climate prediction and how we're using these same tools to study predictability weeks to years in advance. Both I'll talk a little bit about subseasonal to seasonal timescales, but also to multi-year predictability, which is where we're just sort of getting spun up on. All right, so the whole idea with across all of these timescales, so beyond the weather timescale, it's really hard to make predictions, right? And we all know sort of chaos takes over and things get really noisy and messy when it comes to the climate evolution. So we really need to start looking for states of the Earth system or opportunities that are more predictable than others. I really think this is going to be critical to making big advances in this area moving forward. So one example, we're going to start at long time scales and sort of go to shorter and shorter throughout the rest of the talk now. With some work by a former postdoc, Zach Labe, who wanted to study this warming slowdown, also sometimes known as a hiatus that occurred during the 2000s, and said, hey, could we have seen this coming? Could we have predicted this ahead of time? So he took climate model data and trained a neural network to predict, so taking in ocean heat content, to predict whether the next decade would show a warming slowdown or not. Now, I'm not saying this is a cooling or climate change is stopping. I'm saying on top of the climate trend, that there is a slowdown in that trend. In essence, internal variability is sort of pulling it the other way. Okay, so he trains a neural network on lots of climate model output, and then when it makes a prediction, can ask the question, what parts of the ocean heat content were useful in making that prediction? And so it can end up with heat maps that look like this, that suggest that the neural network is learning these anomalous heat content that resembles what's called the interdecadal Pacific Oscillation. Another example, going a slightly shorter timescale now, making predictions of the land surface over the next 5 years. I want to point out, to do this at this stage, we're mostly, not always, but often using climate model data because we have a lot of it. There's other steps to take towards observations. So here, Ben Toms takes in maps of sea surface temperature and has the network predict the temperature over Seattle over the next 5 years. So longer, not your typical weather forecast here. All right, so he does that and it outputs a bunch of predictions, okay? But then what we can do, and this is really important, something that we're doing a lot of right now, is that idea of state-dependent predictability that I mentioned. We have to look for opportunities. We can't always make good predictions. We're trying to use the network to help us find those times. So what we do is on the x-axis, we plot when the network was confident in its prediction, either by some uncertainty quantification method or by looking at, in the classification problem, often it outputs probabilities, look at the highest of those probabilities versus when the network is not very confident, okay? And the idea is if this goes up as you move to the right, when the network becomes more confident, it is also more accurate. It's identifying states that are more predictable. So if you look at all predictions here, the network's not doing so well. It's like 60% accurate. But if you go to here, it's much higher. Less often, but it's when these states happen, it is more confident. So the question is, where is this predictability coming from? And we can start to use XAI to go and make maps of those sources of predictability. So in this case, these are different XAI heat maps. You probably can't see the red dot, but it varies over North America, showing that for different regions of the globe, the network is finding different patterns that lead to predictable behavior of the temperature in those locations. Now, we do this already in climate science by taking composites, but the beauty of this nonlinear approach is it can do all of this at the same time, rather than for each different problem. Furthermore, this is all for the network predicting the same location, but the network, remember how at the beginning of the talk, I said it can learn many pathways of predictable behavior. For the same location, the network has found different sources of predictability depending on that initial state that you put into the network itself. So once again, helping us identify these different sources of predictability. And then finally, Emily Gordon is looking at this too, again, on these multi-year timescales, making a prediction over the North Atlantic, but doing something a little bit different. She's actually predicting probability distribution or conditional probability distribution. So the network doesn't just output what it thinks the sea surface temperature will be over the North Atlantic in 1 to 5 years. It predicts both the mean and the uncertainty or a Gaussian associated with that prediction. Now that's nice because we can draw maps or we can have our predictions have some uncertainty, right? So in this case, the purple prediction is less certain, it's wider according to the network, and the green prediction is narrower. But once again, using this uncertainty, we can look at the states that are most certain or the least uncertain and start to identify that the network actually is most confident about a particular type of prediction. And we can start to investigate why that is. And actually others have found something similar this last year as well, but not using a neural network approach, but doing lots of compositing. So lots of averages under different states to see which were more predictable. And ultimately, she does this for the whole globe and can find that the neural networks identifying that this transport of positive heat anomalies are what are leading to the more predictable behavior. Okay, and finally, I just want to point out something I think is really powerful about neural networks when you're thinking about prediction, which is if you ever want to ask the question, how will our ability to predict the weather change in the future? Like, forget about our technology for a minute, which is hard to do. But as the climate continues to warm, will it be harder or easier to forecast certain things? Maybe the noise has gone up or the signal has gone up. That's a really hard question to answer because we can't run, or we're not running our weather forecast models with the CO2 levels we're going to see in 2070. And we actually did try. ECMWF does not want to do that. Turns out it's a lot of computational cost. So how can we answer these questions? This is one of the fun things I think about neural networks is they act like our little weather prediction model. If we can train it or to do an okay job, we can put it in any world we want, in any simulation that's already been run. So what Kirsten did is she was looking at subseasonal prediction, which for those of you familiar, a lot of our ability to predict on multi-week timescales comes from the tropics. So tropical dynamics lead to predictable behavior in the latitudes in the weeks ahead through Rossby wave teleconnections. And so she looked at the tropical precipitation and trained a neural network that using that information to predict what's going to go on in the Atlantic 21 days later, about 3 weeks out. She trained that using climate model data from a historical simulation and then also from a climate change simulation. And once again, this is the same type of plot where the confidence is on the x-axis and the accuracy is on the y. One of the things I want to point out is if you just on this study and use all of the predictions all at once, it would look like there wasn't any change in predictability because the red and the black lines lie on top of each other on the far left. And you would have said, there's nothing interesting here, moving on. But really, a lot of that's hard to do anyway. But if you just focus on the predictable states in the first place, that's on the far right, you see that the predictability has changed quite a lot over the coming decades in these simulations. That is, these were identified as the more predictable states in the first place, and these saw the biggest changes with climate warming. And then once again, using explainable AI, Kirsten was able to go back and show that it has to do with the effects of ENSO and changing ENSO dynamics on these timescales. Okay, so how am I doing? Good. All right, so some other examples that we're using. So I already said we're using explainable AI for subseasonal to decadal prediction, learning the response to climate forcings, both climate change, but we're also studying solar climate intervention or geoengineering and detecting how the globe might change under such a simulated world. We're using it to actually to develop interpretable and robust AI for climate science. So the actual tool building, I'll touch on that at the very end. And then finally, thinking more with collaborators about societal climate teleconnections and connections. I want to talk a tiny bit about that because it's something new and different for me. All right, so some work that we've done is to try to better start to understand how humans and the earth interact with each other. Lots of people are working on that. This is just a piece that we've done. So there's something called the Human Footprint Index, which has been used in the ecology world for quite a long time now, which is a measure of how much humans are impacting the landscape there. So think of a 0, you can sort of say that purple. 0 is where, pristine forest, if you will, and a 1 is a shopping mall parking lot. And they have spent years. So the most recent product that they put out was in the year 2020. Yeah, there we go. Was in 2020 and was for the year 2013. Okay. And they did this by collecting a ton of data and putting it all together to try to make this one number across the globe. So because they did that, we said, hey, because we have a labeled data set, which is the really hard part, we're going to train a neural network to ingest Landsat imagery and learn to predict that number. Okay, thus we can have a much more up-to-date quantification of that human impact as long as we have Landsat imagery during that time. So the top is our 2000 map. And by the way, this is super high resolution. I just can't possibly show that on my computer. So is the 2000 map, and then we were able to make, in a matter of seconds, the 2019 map using Landsat imagery. Well, it wasn't seconds. It was days of work, but the neural network only took a few seconds, right? Okay, well, that's pretty fun. But this is about explainable AI. It's got to come in here somewhere, right? Okay, so here's one of my favorite locations to analyze during this project. So on the left is the 2000 Landsat imagery. In the middle is the 2019 Landsat imagery. And on the right is the explainable AI heat map showing me why the network thought the human footprint index nearly doubled over that region. And you can see its biggest location it's picking up on was that highway going through, and it turned out the Trans-Sumatran Highway had just been added a few months before this Landsat image had been taken. And it said, hey, there's a big highway here, that number needs to go up higher. Okay, so again, are we learning something new? No, we know that roads are made by humans, but we're gaining trust in our network and making us think that maybe it's doing the right things for the right reasons. We can do this for a lot of different places across the globe, looking at these changes, and it's really fascinating. A fun story actually was this one over here in Indonesia. So the original labeled data set said that was humans really weren't there. And we're going, this is the weirdest geologic thing we've ever seen. It's like, sort of looks like mold growing. Okay, what is this? Our network's wrong. I was like, okay, how should I fix this network? And so it ended up, and my collaborator went in to Google Translate and started translating local newspaper articles from this region to discover this was a secret, secret in the sense that it wasn't totally sanctioned and allowed, gold mine, so for artisanal gold mine. And that in fact, because it hadn't been written down in like the actual Indonesian papers, the original product didn't have it in there. But because we were just using Landsat imagery alone, the network picked it up. That makes it sound like our network's like perfect and amazing. To point out, there are lots of problems with it too that I'm happy to tell you about. I don't want to make it sound like it can do no wrong. But this was a really exciting region. We thought, I think we believe ours more than that label.
So do you get to keep the gold when you?
If only, I know, so cool. But alas, I think not. Okay, so where is this going with the societal piece? Well, actually, this is where my collaborator played a much larger role. I said, sweet data, I love data, that was super fun. It's like, well, let's do something with this. So the paper is actually mostly on the Sustainable Development Goals, specifically number 15, about life on land, and actually looking and seeing how are different countries reporting their progress towards SDG 15, and what is this human footprint index telling us that what is happening. We identified a set of countries that the two seemed a bit inconsistent. We're not trying to say those countries are wrong or misrepresenting information, but the United Nations has stated they need more ways to be able to assess the progress towards these different goals. And this is one example of a possible tool to add to the repertoire. All right, what's that have to do with climate? So far, not a lot. But the next project that we just got funded actually just a few weeks ago, let's see if it's coming. Hold on. Maybe not. hold on guys, there it is, okay, is to take this, we only have 2000 to 2019 right now, but we'd like to have one for every year so we can start to look at trends and changes over time. So we're going to update that and then start to link it with climate hazards and start to assess how climate hazards at different locations have potentially been impacting development in those regions to try to better understand moving forward continued climate hazards impacts across the globe. One of the great things about this product, at least, is that it treats the whole globe equally. We can see everywhere, right? And so we can try and really understand, as long as we know those hazards happen, we can try to understand their impacts. Okay, so this is my final push. We're doing great. All right, so some closing thoughts about, in my view, the things I'm focused on moving forward about explainable AI for climate science. One thing and again, this is a great audience, or this audience knows this, but I really think that climate science has different needs than commercial AI applications. I think LEAP is a great example of people bringing people together and not expecting you can farm all your problems out to one group and they'll just come back with the answer. And I think we really need to continue to develop methods that fit our science. An example is I've already mentioned the state-dependent predictability topic. You know, what if our data, a lot of time I think of my climate data looking something like this. Most of it's noise, but every once in a while, there's something really nice in there. And my job is to be a detective and go and find that nice thing. If you try to fit a best fit line through this data, it's a disaster, right? So what do? We have our graduate students print off a lot of maps, lay them on the ground and stare at them for a few years, right? And hopefully let their brain do all that processing. The idea is, how can we develop AI methods that think of the data in a similar way? And so that's one thing that we've done with colleagues over the last few years, is what we call extension networks. Train networks to ignore most of the data, but they have to figure out which data to ignore, so it can do a better job learning the actual signals that are capable of being learned in the first place. Another is, I presented one explainable AI approach, but there are many. And a lot of us, including myself when we started this project, didn't really appreciate all of the negatives. There are positives and negatives to these, right? All the negatives to some of these methods. So do we trust the methods to help us determine if the network's trustworthy, right? It's a long chain. So Antonios Mamalakis, a research scientist in my group, he trained a network on lots of data on some climate data to count how many atmospheric rivers are in an image. So count, is it 0, 1, or 2? We didn't really care about the answer. What we cared about is using explainable AI to see how they all work on explaining that decision. These different boxes are all explaining the exact same prediction of the exact same network. These are not different networks. This is exactly the same network. So they should all generally look the same, at least if you think if that's how you think they work. But they all give you different types of explanations. And it's really important to understand when each fails, when each succeeds. For example, you can see like gradient shattering when it looks like just reds and blues everywhere. All right, so that's one bit, is really figuring out how these tools work, but also, at least in computer science, where they're doing a lot of the development of this work, the success of the XAI approach is typically assessed by a human looking and being like, there is a cat, the network looked where there was a cat, so we're doing good. But in climate science, we don't always know where the network should have looked. So how do we know that the XAI did the right thing? So Antonios has another paper where we actually made a synthetic fake climate data set where we know the answers and the functions exactly. And he created a data set so we can go in and actually benchmark which of these approaches actually gives us the right explanation because we know what it is ahead of time. And the work that I'm doing quite a bit more now, we have a few projects on this, and this is interpretable AI. Maybe interpretable and explainable are practically the same word. Yes, they are. We can get into that discussion later. But often interpretable is a word used to say it's about like where you design the entire machine learning approach to be explainable from the beginning, rather than after you train it going backwards through it. So the idea is, while explainable AI here helps you know where decisions were, or where to look when decisions were made, it doesn't actually tell you how they were used. This is a great perspective article on this topic. And one of the figures here shows, you know, there's the heat map in the middle for evidence the animal is a Siberian husky. And you're like, oh, it looked where the husky is to determine it was a husky. This is all looking good. But the right-hand side is a heat map for why the network thought it might be a flute. Okay, and the point is they don't look that different. Then you start to be like, well, is this telling me anything anyway? So the idea is to build networks from the ground up that are interpretable in the first place. For those of you who are more familiar with machine learning, I often think that decision trees are a beautiful example of an interpretable method. You can go back through it and see exactly how those decisions were made. Random forests are a little different when you start mixing them all up. But okay, so again, the idea is create AI that explicitly incorporates the decision-making process. So there's a great paper that we built our work off of called This Looks Like That, where it says the way we often determine what type of bird we see out in nature is by going back through our brain and thinking of that type of bird we've seen in the past and saying, hey, this bird's head looks like that other bird's head. I'm going to sort of give it some points for it being a sparrow. Okay, their feet looks like some other bird's feet, with a few more points. And that's how our brains work. So they design a network to do just that. And so the work that we're doing in my group really is one of a few topics is trying to work toward building AI models that mimic the scientists' reasoning. If you will go a little bit backwards now and say, okay, AI can do it all on its own, but I actually want to train it to think more like me, in part because I think it reduces overfitting and ends up having more of the physical constraints built in from the get-go. So that's the thinking. All right, I'm on my last slides. So my big grand statements that I feel like I'm supposed to end with that talks like this. I do think the future of climate science requires the mixing of knowledge, the people in this room are evidence of that, from many fields. And mixing knowledge is hard, and I think machine learning techniques are sort of built to do that mixing. But ultimately, at least we, the we being me, want to know more than the prediction. I really want to know why. That's the fun part. And so I think Explainable AI could be transformational for climate and sustainability research for this exact reason. So thank you.
Thank you, Olivia. With that, my questions. Yeah.
You had a question about like you said
So my
like neural network which are more accurate or more competent, but there was like a dash curve with the downward one. So what was that?
That's the number of samples. So as you start to throw out the less less confident samples, you have fewer samples left. So the idea is, what is that balance between I want the predictions I'll be most sure about versus and accurate about versus I want to be able to make predictions more often.
So if you have a smaller sample size, right? And you discard all the bad samples, it's like less reliable sort of. I mean,
Oh, we still have a ton of data in all of that.
but you said you want to balance it. I mean, like,
Well, that balance is done by different people. So I've had like weather forecasters tell me, no one's going to ever open their phone and say, sorry, we're not very confident today. We're not going to give you a weather forecast. And so that balance, I think, is going to be absolutely user and application dependent. Yeah.
thanks.
Yep.
Hi. So I was wondering how when you predict the year from the map, how you make sure you don't overfit, right? Because I assume you train using maps from every year and then test another map from the same year. And I was wondering how you make sure that you don't overfit and don't pick up like artifacts from like 1 year's recordings, or maybe if you have a map in your testing set that is a map the day after training or something.
Yeah, so in that application, we're training on climate models. And because of that, we actually withheld entire climate models from training that acted both as our validation and then a totally different set of climate models that acted as our testing members. So that was one way you combat that, because in that case, we never had autocorrelation issues. So an entire simulation with these are part of training, validation, or testing. On top of that, I will point out, we're putting in maps. There are a lot of grid boxes, no matter how you slice and dice the globe. So that's a lot of predictors or features in the first place. So here you're using dropout or ridge is critical, or the whole thing will explode. Yeah.
And when you make a mistake, does it make sense when you look at like where the network looked at, or is it completely random?
That setup is pretty darn good. So if you look, I mean, it's all relative, right? But in this case, it's a regression problem, and it's only off by a few years. And so in that case, it makes absolute sense. When it does the worst is early on in the 20th century, but again, that makes sense because that's before the force signal is really showed up. Yeah.
Thanks for a great talk. I have a question about the explainability. Many times relying on visual inspection of the explanation. I think easier to say interpretation, not explainable. So I wonder where someone on that for another application is how do you systematically evaluate the explanation, even when you can now visually make sense of it? Have you thought about that in addition to this look like that? Because the bird is a good example of you're trying to recognize something and you recognize there are some parts of a system that should look similar, but what if we're dealing with a system that you don't have that kind of segmentation of parts? Then how do we make progress in measuring explainability, measuring interpretation in a systematic way so that we can create meaningful feedback to the machine learning system?
Yes. Okay, so we thought a tiny bit about that, which is, I think I mentioned very briefly, Antonia Tomalakis in my group, we had the same question. How do we even measure how these are different or who's doing a good job? We know they're different. The explainability methods are giving us different answers, but how do I know which one's right? And that's where he came up with a data set that he made that looks a lot like surface temperature of the climate system, but it's not. He actually just made up that data where he knows the functional form exactly. He can create millions and millions of samples to train his network until it has near perfect. I think this has 99.99% accuracy kind of thing. And then from there, we can then try and evaluate the different explainable AI methods since we know the correct answer, if you will. That is what we have come up with, trying to actually quantify that explainability. In terms of the interpretability, so there are lots of different ways people have approached this. There are some examples or types of networks where the user goes in ahead of time and says, we know birds have distinctive feet, tails, necks, and heads. And so you actually tell the network sort of ahead of time, these are the features you want to look for. But I think this is sort of getting at your question, which is, what if I don't know to look at necks and heads? I don't even know what the things are I should be looking at. That's where this particular network, this looks like that, does it. The network learns the features that are important.
Say that there are local features. What if there's no local features?
So, sure. So for our work, there will always be a local feature. The stuff we're doing with the climate system, we're looking for patterns. Yeah.
It's good at looking for local features, but when you miss the non-local feature, there are local and non-local features. There are highly dimensional non-linear features. So relying on this to that may miss that.
So this is done in the latent space.
No, I read the paper. Right?
Yeah. Oh, okay. So, well, in that sense, the non-linearities, at least from, you may know more about this than I do, which is very possible, but I'll just point out that this looks like that is not done in visible space, right? It's done in the latent space of the convolution of the network. And so at least insofar as it looks like that in that latent space, I think this will still work.
Can I make a follow-on question? How then do you know that, do you have any confidence from that example that it would be that if you say, oh, this approach works well and that approach doesn't, that would be generalizable to other situations? Like how then do you evaluate going from your created sample to real world? Like how do you make that jump?
Yeah, so at least for our problems, we're not trying to develop new methods that work for every data set. So we're really focused on subseasonal to decadal prediction. Because we know that's the problem we're focused on, we understand the system and sort of what it's going to look like. So our first work, we made up fake synthetic data and showed it did what we thought. Then we went to real world data, the Madden-Julian oscillation. I actually looked at that, showed it did exactly what we thought because we knew the answer ahead of time. And now we're working on actual prediction problems where we're not quite sure, but we think those pieces may be in there. So I don't have an answer other than we're doing it iteratively. Like so many things to gauge trust, you need to do lots of little things over time. Yeah.
Great talk. Yeah, I had a question. I've seen that many times, and every time I have new questions actually. And I was thinking, because related to the point about validation, when you're trying to predict the years, right?
Yeah.
And I was always curious, why would the models be so close to the ops, right? I mean, it's like mind blowing.
Yes.
Right? But then you're bringing up the fact that the validation is actually done on a different model. So basically what you're learning might be, and I'm just making that up, you can correct me, but maybe the fact that the model is learning where models are wrong, you know, because you're bringing up another model. So you know, like the biases in the models, like in space, right? And at the same time, you also know where there's information as well. So it's kind of a mixture between where there's real information and where you should never trust the model.
Yes.
Right?
That is, it's not just that other models are in validation, it's that our training set has multiple models too. So that is exactly right. The network isn't just looking at where there's a good forced response or the signal to noise. It's also saying, never look here because our climate models have no idea what's going on, or our climate models disagree so wildly that that is not a good place to look. And that is why I think it's amazing still that observation works. It says that somehow by learning across and finding almost like a consensus of where, like, well, if all the models agree, maybe something's right. We know that can get us into a trap too, right? All the models can have the same bias. But in this case, it's identified the places that are at least consistent across climate models happen to also be consistent with OBS. I think that's pretty cool.
Yes, very cool.
Because it's not just signal to noise, which doesn't incorporate that, but it's also not just model uncertainty. It brings all of them together and works. And actually, I mean, I didn't show precipitation here, but precipitation, a much harder variable, also does okay.
Maybe a quick follow-up to
Yeah.
that. I mean, it would be very interesting to know what are we missing, like in the ops, where is the information? So for instance, one thing I always had in mind, like article amplification, right?
Yes.
And for instance, right of notice group saying that every day you can see climate change, right?
Yes.
So is there something that we're missing in models, right? That you have a lot more, like, for instance, we could have seen climate change coming up a way earlier if we had better models, basically. You know, if you could change your models and now all of a sudden you have an LES of the world.
I don't know. I think one of the things that we are missing, well, not missing, people, really smart people think about this, but a lot of the way we evaluate our models and look at these comparisons really is point by point. And I think both the Nudie paper, this work, are leveraging spaces that are separate from each other and saying, but if it's warming here and here at the same time, that means something very different than just warming here or here alone. And both of these methods take that approach. And I do think that we need to incorporate that more when we think about our climate model evaluation. Yeah.
Thanks, Phoebe, as always.
Yeah,
Wonderful
sorry.
talk.
Yeah.
So it's a little bit of a follow-up on some of the work that you show in terms of, you know, long-term predictability,
Yeah.
which seems to be kind of coming up from the North Atlantic and, you know, some places where we know there is a strong signal, but it's where the models are doing the worst job ever, right?
Yeah.
They get the natural viability wrong, and the forced response is also all over the place because there is a mix between viability and forced signal.
What are we going to do about it?
Yeah.
Yeah.
Well, I mean, is there something we can pick up from that actually?
Yes, so two levels to that. So first of all, in the one case, you could say it's sort of hopeless because what we're doing right now is playing in our sandbox, trying to see if there are methods that work for this problem. And to do that playing in the sandbox, our sandbox is the world of climate model data because we have a lot of it and I don't want to be constrained by not enough data right now. At the same time, they could work all nicely, but the models are such junk that what's the point? So one of the approaches we are taking that others are as well is I have a postdoc, Francis Davenport, whose whole project is just focused on the transfer learning part to think carefully about how we do transfer learning for multi-year climate prediction. So again, we're not going to jump straight to the OBS because my guess is we'd fail anyway. What we're doing is we're taking two different climate models and we're going to transfer from one to the other where we know their ocean dynamics are a little different. We're going to see how do we interpret those results, go through nice and slowly, and then move on. So that's what could it fail or yeah, I actually have no idea if this is going to work given these biases, but I feel like we're at the point now with these tools that we can try.
It's also a great way to actually figure out what the models are doing similarly and what they're not. Right?
Exactly, because then using XAI and interpretable AI, you can go back and figure out through that transfer learning process, what was learned, what was transferred, why were the weights tweaked the way they were to go from one model to the other or from one model to obs. That's the definite ultimate goal. I hope it works. So I'd love to write that paper, but
Thanks for the talk. I have a question about extremes. So I work on energy system. We care a lot about extreme events. So going back to your example about predicting years from the temperature.
Yep.
So of course, my gut feeling is that if you feed that into the neural network will focus on the location where it has the most stable global warming. But likely we'll ignore places where there might be extremes. 1 year is very hot, 1 year is very cold. So what's your take, like if we want to apply a similar method but focus more on finding where extreme is more likely to happen or even to try to predict future extreme events. Yeah.
so I don't think this method is helpful for predicting future extreme events. However, I think when you're saying extremes, 1 year's hot, 1 year's cold, I mean, to be clear, climate change is making everything hotter. Okay, so the cold is just that natural variability, so it's a noise. So you're saying, hey, where you have big noise, maybe it won't focus there. And indeed, yeah, if the signal is small and the noise is big, it won't. However, in Jamin's paper, he then went in and instead of inputting precipitation and temperature, he input maps of extreme precipitation. So some high tail of how many days per year do you hit some high tail, or how many millimeters above X, Y, and Z. And so those are the maps he puts in and does the exact same problem. So you don't have to put in like a mean variable. You can put in anything you want, really. Does that make sense?
Yeah.
And so in that case, he is focusing on where are the extremes helpful in predicting the year. Yeah.
Okay.
Yeah.
Okay, we're gonna take one question from online, from David Gold. AI is about using the data to uncover insights, although choices have to be made about model architecture and expertise can be encoded into the loss function choices. Do you see a role in using structural causal models, which involves information outside the data, for guiding choices in model architecture and the data exposed to the input layer of the models?
I feel like that's right. An easy one. Yes. I mean, I think that's a great idea. I actually, some of the work coming out of like Pierre's group and Veronica Hearing's group are like thinking about how do we merge like causal discovery and graphs with neural networks and put those together. Again, this I think falls very broadly, and maybe this is a stretch, into the more of this interpretable side of trying to force the network to learn a certain way, or even broadly into that box I put up, trying to mimic how humans are reasoning through these, because we have been trained to think through these causal links. And I personally am running away from the whole concept of put a big network on the job and hope it does a good job. And I'm less interested in the accuracy and more interested in making sure it gets it right for the right reason. And I think that's a great way to attack it. Yeah, I mean, that stuff's awesome.
Okay. Is that another question from here?
Okay.
Great talk, maybe. One of the issues we are dealing in our group a lot, we're very interested, is like common biases in the models. For instance, one of the, probably you have to know very well, the mean Pacific bias and how that influences a lot of things. So then all your models are doing the same thing, or incorrectly,
Yeah.
or they all have a messed up MGO, they're going to messed up your S2S forecast. So how do you have any ideas how to work on that?
Yeah, so so a few things. So one, I think S2S is a good example where I think we have one paper where we have just enough data that you can actually argue that using machine learning is okay on OBS alone. So one answer is just run away from the models and focus on the data that maybe we believe more. And I actually think there's a lot to be done there. In our groups, because we're really also trying to build methods that, again, try to mimic the way we think, we want to play in this big sandbox, but we could be just getting absolute garbage out in terms of the actual predictions, sure. But I think it's still a useful sandbox to play in. With that said, in that transferring of knowledge from the climate models that could be wrong for that we know, and they're all wrong for the same reasons, to OBS, I do think that's where sort of this transfer learning approach that I mentioned what you do is you train on data that you have a lot of that's imperfect. Well, we got that. Okay. And the idea is then you fine tune that model on observations where you have a lot smaller. So I like to think like if you're scaling the mountain, you get most of the way up the mountain. I should probably go the other way. Losses go down. Yeah. Okay. We're going down the mountain. Okay. So we get most of the way down that mountain using those climate models. And at the last little bit, we really tweak those parameters to make it better for the obs. I think, I don't know if it's going to work. We have some examples already in the literature where it did work. But I think that is a good method moving forward. And then, of course, the standard ways that machine learning can be used for making climate models better that have nothing to do with what I talked about, like parameterizations and just actually making the building blocks. But I mean, that's great. So I think there's a lot of different ways to come in. But no, I don't have an answer.
Okay, well, I think we'll leave it there. We'll thank Libby again and hope everyone's doing